So now we have the power to kick out some basic infinite outputs, or at least in theory infinite, as long as the computer could run forever. These outputs are usually some form of sequence. So we've dealt with the sequence of natural numbers, we've dealt with the sequence of integers, right? And now we're going to look at some more sequences that we can generate by making slight modifications to what's actually quite a powerful piece of code. So, introductory sequences. As follows. The first four sequences are powers, are of positive powers. Then we'll have something called the harmonic sequence. Harmonic sequence. 1 over n. Don't know where I wrote 2. And then the next three are exponential. And I would pay quite, for my students at home, yes, I would pay quite close attention. Pay close attention to these particular sequences. They might be very helpful to you. So let me give you these example sequences. This will take a minute for me to copy out. Such as life. If I can get them to stop misbehaving. There we are. All right. So our first sequence, I'm going to name our sequences. Don't worry too much about what the names mean so far. It will start to sort of make sense. But in general, I don't want to break down the relatively complicated naming formulas for sequences. 1, 2, 3, 4, 5. This one, however, you guys all recognize this is just a sequence of natural numbers, right? N squared. This time we take each value and we multiply it by itself. 1 times 1, right? 2 times 2, 4, 9, 16, 25, 36, 49, 64, and away and away and away. We can obviously do this as many times as we like, right? And this gives us a whole bunch of potential sequences that might be useful under certain applications. So 1 will be the first again, and then we have a 2 cubed, 3 cubed, etc., etc., 4 cubed. It's nice having this natural sequence here because it provides a sort of reference for our following sequences. In fact, we're often going to do this just to make our lives simpler. Right? Same sort of deal here. 64. Let me fill in these numbers for you. 125, 216. Oop, getting a little cramped. 343, and 512. All right, I'll do this one more time for n to the 4. 1, 16, 81, 256, right? 625, 1, 2, 9, 6, 2, 4, 1. Powers of, the values related to 7 are always interesting to me. Never quite expected. As promised, doing it again. As promised, what follows is the harmonic sequence, which is 1 over n, so 1 over 1, right? It's just 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5. This is quite an attractive sequence when written out by hand like this. Quite an ugly sequence when we try to give it to a computer to calculate, because they're not so good at this fraction thing. So usually they'll start generating smaller and smaller decimals, and then quite quickly they'll run out of memory for the decimal spaces that are available to you, and the code will end up at 0. Let's look at a couple more options that are also potentially available. 1 to the n. This is a sequence we should all recognize, right? 1 to the 2. Each time we're just multiplying things by 1, more and more and more and more and more. This will go on forever. 2 to the n, however, actually gives us some interesting behavior. Here we get 1, 2, 4, 8, 16, 32. In fact, there may be multiple ways of generating this code. 64, 128, and on forever. Again, we can increase this as many times as we like. So here we have multiple options for many different potential sequences that we can very easily generate with our code. 1, 3, 9, 27, 81, 243, 729, 2187. So here are some nice, interesting sequences. Now you might think it would be quite hard to write code to generate all these, but it's actually quite easy. We can adapt our infinite code to generate all of these. As should be clear from the fact that we can order these sequences by n. Right, so we've got this nice comfortable ordering here. For every value in n, well, we're already generating a corresponding value for all of these guys. So if we can just figure out how they relate to each other, then we can produce all of the desired values of n. This ends up being shockingly simple to produce using a piece of code, and I'm going to use the power of a print statement to do it. X equals 1. We're going to use while true, which we'll remember just runs our while loop forever. You're going to indent properly, and remember we got to have our double dots here in order to make sure that the while loop actually works. First, we're going to print x. Then we're going to print x squared. Then we're going to print x cubed. Then we're going to print x to the 4. Then we're going to print 1 over x. Then we're going to print one to the x, 2 to the x, and 3 to the x. We got to remember though, this isn't quite an infinite loop yet. X equals x plus 1. And there we go. That relatively simple little piece of code will generate all of these sequences. Each time this runs, we start at 1. We generate our first value, 1 up here. If you look at it, we go through 1 squared is 1 to the cubed is 1 to the 4 is 1 over 1 is 1 to the 1 is 1, 2 to the 1 is... Two to the 1 is actually 2. So interestingly enough, these last two sequences we generate without the initial term. And the explanation for that is, I think, quite straightforward. And the fix to the code is also quite straightforward. We'll notice that technically speaking, with our 1 to the n term, we're actually starting at the second term of the sequence as well, if that serves as any particular hint.